After formulating the model, finding solutions, applying the model to make predictions, we may need to understand the stability of modeled equilibria. Determining the equilibria of a system is one of the most important steps in analyzing a dynamic model. A system at equilibrium does not change over time, so a particular value of a variable is called an equilibrium variable if it never changes in time. At an equilibrium, in discrete time models, the values at nt plus 1 must always equal that of the previous time step nt for each variable. Equally, the amount of which a variable changes must be 0, so in a continuous time model, dn on dt should always be 0. Dynamics in equilibrium have typically a constant steady state, but can have also stable limit cycles. Out of equilibrium conditions are divergent, so infinitely expanding, or can be chaotic. In order to know when equilibria are stable, we perturb the system and quantify how the imposed small deviations from the equilibrium grow or shrink. If they grow, the system will deviate from its equilibrium and is therefore unstable. This is best visualized by a ball on the top of a hill. If the ball is pushed a bit from the top, it will move further down and never bounce back. Alternatively, if the ball bounces back, for instance when it is in a valley, the equilibrium at this valley point is called stable. Every deviation will decay in the next time step. This is the asymptotic stable position. When the ball is on a flat surface, so when equilibria are present across the entire parameter range, the system is neutrally stable. When the ball is on a flat surface, so when equilibria are present across a parameter range, the system is called to be neutrally stable. We will during this lecture show how the stability can be assessed by means of analytical and graphical methods. We start with simple one-equation models. Whenever a model reaches an equilibrium, it remains a question how the model behaves outside its equilibrium. Will it approach or will it move away? Consider therefore a population that starts at a point nt, that is very close to its equilibrium point n. If that point represents a certain perturbation, let's say epsilon, then a point at that distance, epsilon t, will have a value equaling nt minus the equilibrium value n. Its values, either epsilon being larger than 0 or smaller than 0, will tell us whether the distance to the equilibrium shrinks or grows over time. Now, let's for ease of reading drop the t notation and consider a differential equation for the displacement, epsilon equaling n minus equilibrium n, from the original equation for the original variable f on n. By definition, any change in the distance from the equilibrium will be dn minus n equilibrium on dt, which becomes simply the change in n on time because the equilibrium is a constant. The right-hand side does not contain the perturbation anymore, but we can substitute it by the differential at equilibrium point plus the perturbation. We can use a Taylor series to solve this differential equation around equilibrium when perturbations are small and obtain a linear approximation, being delta epsilon delta t, the function of the equilibrium, plus the partial derivative of the function at that equilibrium point times the perturbation strength. We can use Taylor series to solve this differential equation around equilibrium when perturbations are small and obtain a linear approximation as fn being the function value at equilibrium, plus the partial derivative of the function at that equilibrium point times the perturbation strength. The derivative represents the slope of the recursion equation with respect to the variable n evaluated at its equilibrium. This partial derivative is called the Jacobian. To simplify, we replace this term by lambda. Or, since the function value at equilibrium is 0, we get delta epsilon delta t equaling lambda times epsilon t. And this can be solved analytically as seen here. The perturbation will thus increase when lambda is larger than 0 and shrink when smaller than 0. Negative values for lambda, thus the partial derivative, will represent stable equilibria, positive values unstable ones. We thus have a recipe to analyze the stability for an equilibrium in a continuous time model. Consider differential equation dn on dt. As step 1, we need to differentiate the function with respect to n. Then, replace every instance of n in this derivative with the equilibrium value n to obtain the partial derivative at this equilibrium value. In the third step, we will define lambda, determine its sign and magnitude, evaluate the stability of the equilibrium so as the conditions where lambda becomes negative or positive, and if needed, we repeat all these steps for each equilibrium of interest. Or for a worked out example, we take the Lotka-Volterra population model. We know the system has two equilibria, 0 and k. We take the derivative using basic calculus, which is r minus 2rn on k. We plug in equilibria and find the derivative lambda to be r or minus r, hence being positive for the 0 equilibrium and negative for the k equilibrium. Remember, r is always larger than 0. So, the equilibrium is stable for n equaling k. Now it's up to you. Practice this for the harvesting growth model and the Levin's metapopulation model. We can also use graphical methods to understand the system dynamics, so by using R to plot our function, finding the roots, and testing their stability. So let's translate the earlier method more visually. When we plot a differential equation, we plot change rates at every variable of the variable. Intercepts with y equaling 0 represent the roots, hence equilibria. The partial derivative of the differential equation at the equilibrium, remember the Jacobian, then gives the slope of this rate of change around the equilibrium, and when negative, like n1 for instance, clearly indicating a stable equilibrium. In case of n2, Jacobian is positive and the equilibrium is unstable. So, as a first step, we plot the derivative here for a fishery model. We determine the directions of change and the stability of the roots. Arrows pointing towards a root indicate a stable equilibrium, diverging arrows an unstable one. We can thus indicate a domain of attraction for every stable equilibrium. Remember, the number and types of roots is of course very specific for every function. And as a last step, we can plot roots in function of the parameter space and indicate whether they are stable or unstable. We refer to such plots as bifurcation plots when the parameters, as are here, may result in different roots and their condition. You can find the code for running all this in R here. Run this and try.